Hello everyone, my name is Damjan Becirovic and I am one of the engineers at Semaphore. In this session, we are going to take a deeper look at Plumber, the core component of Semaphore responsible for processing and orchestrating Semaphore pipelines. To start, let's take a look at the agenda for today's talk. Firstly, we are going to do a short intro through the main Semaphore concepts, which are pipelines, jobs, and agents. This part is intended for any listeners that are not yet too familiar with Semaphore. After that, we are going to take a zoom-out look to see what happens from the moment when you push your changes to your Git repository until your pipeline and jobs are running. And then finally, we are going to zoom in on the pipeline processing component, the Plumber service. We are going to examine the main principles and requirements that guided us in creating this system that is processing thousands of pipelines every day. We are going to look into the Plumber's architecture and examine the main points of its implementation. At the end, we will see how the system works on a simplified example and explore how we can extend it with new functionalities. So let's start with the first point of explaining the main Semaphore concepts. The rectangle that you can see in this image, called build and test, represents a Semaphore pipeline, which is an organizational unit that allows you to model your whole CI process. The pipeline consists of several blocks: setup, analyze code, and tests, which are, in this example, run sequentially one after another. The blocks can also run in parallel or depend on multiple blocks, which allow you to model complex use cases. The blocks consists of one or more jobs that are all run in parallel. A job is an executional unit that actually runs your tests and commands. Since we are now familiar with the main Semaphore concepts, we can take a look at what actually happens from the moment when you push your code to your Git repository until the first tests are run in Semaphore jobs. Now let's take a zoomed out look at what happens when you push your code to your Git repository. If you have seen the earlier presentation by my colleague Radoslav, this might be familiar to you. So, when you push to your Git repository, your Git provider will send a webhook to Semaphore, and it will arrive first to the part of the system called hooks processor. The hooks processor will validate and verify that webhook and transform it to a format suitable for internal processing. Next step in this process is called the pipeline processor, and this part of the system is the main focus of this presentation. There, we will fetch a YAML definition of that pipeline, create a pipeline based on that definition, and orchestrate the execution of blocks and jobs. The next part of the system is a job processor. It is responsible to prepare and manage execution of individual jobs on suitable agent machines. Finally, we have an agent pools in which the jobs are actually executed. Those are the fleets of machines that can be hosted by Semaphore or self-hosted by Semaphore users. Now that we are more familiar with the whole process, we can zoom in on the pipeline processing part and its main service called Plumber. We can start with defining the functional requirements, or what actually means to run a pipeline. In order to start a pipeline, we must first fetch a YAML definition of that pipeline, verify it, and process it. Next step is to validate conditions for running that pipeline and its blocks. The pipelines and blocks can be conditionally run based on criteria like the branch name or result of the previous pipeline in the workflow chain. Once the pipeline is cleared to run, the blocks need to be started in proper order based on their dependency graph. The jobs from each block are then passed to the next service and processing system. While jobs are running, the Plumber is keeping track on execution time limits to prevent stuck jobs from incurring additional expenses. Also, if the user stops the pipeline manually, all running jobs need to be terminated properly. Finally, once pipeline is done, other services need to be notified. Now, let's see what are the non-functional requirements for the pipeline management system. The availability is the main non-functional requirement for the Plumber service. Our users rely on Semaphore to deliver their code, and any disturbances in the delivery system can have significant impact. The scalability of the system is equally important, especially during peak times when many developers are pushing their changes at a similar time. The solution system also needs to be fault tolerant. So one malformed pipeline cannot stop the processing of all other pipelines from all other users. As the requirements evolve during the time, it is also important for a solution to be easily extensible to cover new use cases. Finally, there can be no false positives in the pipeline test results, since that can lead to our users delivering code with known issues. Now, let's see the architectural decisions we made when designing Plumber to cover these two sets of requirements. Architecture of the Plumber component closely follows overall architecture principles of the whole Semaphore. If you have watched the presentation from my colleague Radoslav, this will be familiar to you, but it still needs to be reiterated here in case someone missed that presentation. We are relying on microservice architecture since it allows us to develop and scale different parts of system independently. For deployment platform, we are using Kubernetes, and it allows us to seamlessly scale and update our services. The Plumber service is developed in Elixir programming language. Elixir is a modern language for functional programming built on top of the Erlang language from Ericsson Telecommunications Company. Both Elixir and Erlang have a built-in support for concurrency, distribution, and fault tolerance. For database, we are using PostgreSQL relational database as the main source of truth, since it allows us to keep the data consistent through atomic transactions. Finally, RabbitMQ is our messaging broker, and its primary function is to reliably publish messages to all interested microservices. When it comes to implementation, the Plumber was based on finite state machine mathematical model of computation. Per this model, the system can be in one of the finite number of states at any given time. The finite state machine system can change from one state to another in response to some event or input, and this change is called transition. If we check the example of a finite state machine system on the image on the right, we can see that there are three states: work, home, and bed. The arrows represent events that transition the system from one state into another, like taking a train from work to home or going to sleep in bed. This model is also a good fit for pipeline processing because pipeline's lifecycle can easily be mapped to a finite number of states with one starting and one final state. We can then implement a different worker to handle each specific state, which reduces complexity of the system. These workers can be triggered periodically or on outside signals, like specific job being finished. Here we see a simplified example of managing pipeline's lifecycle with state machine model. As previously, we have one starting state, and here we call it initializing state. When pipeline is created, it will start in this state, and here the worker will fetch the YAML configuration for that pipeline, process it, and create all needed subcomponents like blocks and jobs. The pipeline will then transition into the next state, called pending state, where the worker will validate the conditions for running that pipeline. If all conditions are satisfied, the pipeline will transition into the running state. Here, the execution of pipeline blocks and jobs will be orchestrated, and pipeline will remain in this state until all of its blocks are finished. Once all blocks are done, the pipeline will transition into the final state called done state, and the result attribute of the pipeline will be set to one of possible values, like passed, failed, or stopped. Now, let's take a closer look at the implementation of the worker process that will perform actions necessary for a specific state. Here is the simplified implementation of the worker in Elixir-based pseudocode. We are calling these workers loopers because they are looping through all pipelines in a specific state and executing them one by one. This worker is based on a Gen server, which is an Elixir abstraction over the process that receives and responds to messages. The Gen server will be the part of supervision tree, which is a mechanism in Elixir that ensures that any processes that crash are then restarted. When the worker starts or restarts, it will first execute the init function. This function will send the wake-up message to the same process with a configured delay. Once the message is received, it will trigger the handle wake-up message function. Inside this function, we will first perform the state-specific logic with doWork function, and then reschedule the next iteration of the work by sending another wake-up message. With this pattern, we get a worker that is periodically executing the state-specific logic. If we take a closer look at the doWork function, it consists of 3 steps. Firstly, we select one pipeline in the specific state and lock it by setting a flag in database. Next, we perform state-specific logic on that pipeline. This is the only part that is different between looper workers for different states. Finally, we transition the pipeline into the next state and unlock it by resetting its flag in database. Now, there is one problem with this approach, and that is what if something breaks in the state-specific logic step. As we said previously, the looper process will be restarted by Elixir supervision tree, but the particular pipeline will remain locked in database. To solve this problem, we can look at all pipelines that are being locked for longer than expected as being in the new stuck state. We can then implement the worker that will loop through all pipelines in this stuck state and try to recover them. As illustrated on this image, pipelines in all states except done state can end up in a stuck state. The stuck state worker will unlock those pipelines and return them into original state to retry the state-specific logic. If the original problem is still existing, the pipeline can end up in a loop between original state and stuck state, so we need to add a circuit breaker to transition the pipeline into done state after several failed attempts to recover and reprocess that pipeline. Now let's take a look at the implementation of this recovery worker. As we can see, the implementation of this worker looks very similar to regular looper workers for other states. We have an init function that schedules a work by sending a wake-up message with delay. Then we have a handle wake-up function that is executed once the wake-up message arrives, and it again executes state-specific work and then reschedules the next iteration. Finally, we have the doWork function. And here the main difference of the stuck state worker from other worker is. Here we will first find one stuck pipeline, and then based on the number of failed attempts to recover it, we will have 2 different behaviors. If pipeline was recovered less times than the limit, which is 5 in this example, we will transition it into original state after a backoff delay, and also increase the counter of recovery attempts. The backoff delay is increasing exponentially with each retry to allow enough time for resolution of any transitory issues that might have caused the pipeline to get stuck in the first place. On the other hand, if we have reached the limit of recovery attempts, the pipeline will be transitioned to done state and result attribute will be set to stuck. This approach allows Plumber to self-recover from any transitory issues, but also prevents the pipelines that are failing due to other issues from negatively affecting the rest of the Plumber functions. Now that we have seen how pipeline processing is working based on state machine model, let's see how that model allows us to easily extend functionality of the Plumber. Let's start with the simplified pipeline state model and examine how we would add the functionality of stopping a pipeline execution. User can stop a pipeline manually via API or UI action in any point of the pipeline execution. If this happens while pipeline is in initializing state, we can easily just transition it to the done state, since no jobs are yet running outside of Plumber. If pipeline is stopped while in pending state, the behavior is the same. We can just move the pipeline to the done state. But if pipeline is stopped while in running state, we have to first make sure that all running jobs are stopped before we can transition the pipeline to the done state. We can easily achieve this by introducing the new state called stopping state. When stopped in running state, the pipeline will send stop requests to all running jobs and transition into this new stopping state, where it will remain until all its jobs are done. After that, the pipeline can safely be moved to the done state with result attribute set to stopped. Now let's examine a different example of adding a new functionality to Plumber. We will again start from a simplified pipeline state model and consider how we would add pipeline queue functionality. Consider a case where a user pushes new commits several times in a row in a short amount of time. Each of those pushes will trigger a new pipeline, and if those pipelines are using any shared resources, then they should not be executed in parallel. Instead, they should be put into a queue and executed sequentially one after another. We can easily add this functionality by adding a new state called queuing state. We will modify the pending state to first check if any pipelines from earlier pushes to the same branch are already running. If there are no such earlier pipelines, the pipeline in question can transition directly into the running state as usual. On the other hand, if some earlier pipelines are already running, the pipeline will be transitioned into the new queuing state. In this state, the looper will check if all previous pipelines are done, and once that is true, it will move the pipeline to the running state. To conclude this presentation, let's recap how the Plumber implementation we have is solving all functional and non-functional requirements we defined at the beginning. For managing pipelines, we have a standardized solution based on finite state machine model, implemented and structured through the set of looper workers. The availability goal is achieved by relying on Elixir supervision tree to restart any failed workers, and Kubernetes liveness probes to restart any pods that have failed completely. In case of scalability, we can easily scale vertically by starting multiple Elixir looper workers within the same Kubernetes pod, and horizontally by adding more pods. For fault tolerance, we rely on built-in Elixir tooling like supervision tree and custom solutions like our workers that are handling stuck pipelines. And finally, for extensibility, we saw that we can easily extend the functionality by introducing new states into the pipeline finite state machine model. That would be all for today's presentation. If you are interested to learn more about the Plumber, all source code is open source on GitHub at semaphore.io/semaphore, so you can take a look there. If you have any questions, join us on our Discord server. Finally, if you have liked the presentation, consider subscribing to our YouTube channel to see if more interesting videos in the future. Thank you for your attention.